Draw the Lewis structure of the following compounds and determine if the bonds in each molecule are polar, nonpolar, or ionic. Provide proof in each case. Kind of sounds like a lot. We just break it down one at a time. The first thing we need to do is draw this Lewis structure right here. So I look down here. The first thing I want to ask myself, is this a metal with a nonmetal, or is it a nonmetal with a nonmetal? In this case, what that's going to tell me is that would make an ionic compound. That's what it asked me to determine here. Or is this one would be a covalent compound? That's going to determine how I draw these structures. So in this case, I have two nonmetals, and so the structure is going to be shared pairs. I don't know if they're polar or nonpolar yet, but I do know they're covalent, so they're shared. Easiest way to probably do this is to draw your Lewis dot for the atom. Okay. Paired electrons are not available for bonding. Those are called lone pairs because they're by themselves. But single electrons don't like to be like that. What they want to do is they want to pair up. And I recognize that this would be a good arrangement, but I don't really draw it like that. We draw it like this. And these ones I haven't bonded yet. And that line represents a shared pair. So bromine has 2, 4, 6 of its own, plus 1 there, which is this guy here. 1 there is 7, but sees this one as well because silicon's sharing it, so it sees 2, 4, 6, 8, sees 8 electrons, octet is satisfied. If we did that for the same for all of those three, what I'm going to end up with is SiBr4, which we can come up with because I was told, I have SiBr4, or just because I only have silicon and bromine and I need everything to be satisfied. So each bromine we showed has 8. What about silicon? Well, silicon sees the 1, 2, 3, 4 that it owns, 1, 2, 3, 4. But it also sees each one of these ones from bromine that bromine is sharing. So it actually, for each line, it sees 2. 2, 4, 6, 8, octet rule satisfied. So that takes care of my structure. Now what I need to do is determine if the bonds are polar, nonpolar, or ionic. Well, I know they're not ionic because they're covalent. Delta chi, which would be equals silicon, or in this case bromine is higher, minus silicon. If you screw that up, just erase it and put the higher one. I had to look these up. Bromine is 2.96, silicon is 1.9. The difference is 1.06. That 1.06 falls down on my chart between 0.5 and 1.7, so that means it is polar. The bonds are polar, so that's what I would write. The last step that I have to do is I got to show which one of those has a stronger pull. Well, bromine has a higher electronegativity, and so it's going to pull electrons closer to it. So each one is kind of negative, and the silicon is kind of positive. I've drawn the Lewis structure. I've determined if the bonds are polar, provided proof. This is proof here. And then I've shown that I know what that means and put on my partial charges. Okay, in our second example, we've got to look again if we have a metal and a nonmetal, or two nonmetals. Sodium is a metal, sulfur is a nonmetal, so I'm thinking this is going to be an ionic bond. Because of that, there's going to be a transfer of electrons, so I'm going to start with my Lewis dots again, but I'm going to look to transfer any electrons that would work. So sodium wants to get rid of 1. There's a good place for it to go. But sodium then becomes, we don't have to show all this, I could have just drawn straight the final answer, but I'm going to show you how we get it. Becomes that it's happy. It doesn't do anything else. It now has full inner shells. It's good. Sulfur is happier, but not happy because it's got an unpaired there. So I need another sodium to donate, and that means that sodium is also there. And now sulfur has 8 electrons, so sulfur is also satisfied according to our octet rule, but it has 2 extra negatives, this one and this one. Sodium lost, sulfur gained, Na2S, we have Na2S, it seems to work. How do I prove it? Because we still need to prove. To my electronegativity difference, in this case it would be sulfur minus sodium. I'm honestly not sure what the numbers are. I'm guessing that sodium is somewhere in the 2.6 range and sodium is somewhere around 1 or less than 1 even. Putting this into very polar or ionic. Either way, if it's in the very polar range of 1.7, it's still good enough because this is a metal and a non-metal would trump my very polar electronegativity. Electronegativity is a check, not the rule, so we follow the rule first. But I think it would probably come out pretty close to the ionic. N2 is a trick one, sort of, because it's non-metal with non-metal. N bonded to N. So if you have one thing, but they're both non-metal, so diatomic, it's going to be covalent. This will be perfectly covalent, as we'll see in a minute. Nitrogen is 1, 2, 3, 5. This nitrogen is also, I'm just going to mirror it, 5. Those can pair. Those can pair. Those can pair. I don't need to show any of that, but what I end up with at the end is actually 3 bonds between nitrogen. Is very strongly bonded to each other. I'm going to clean this up just so you look at it. So that's what I would come up with. How did I get that? I got that from those 3 unpaired electrons on each one sharing. 2, 4, 6, 8 for this nitrogen. 2, 4, 6, 8 for this nitrogen, because each one of these bonds is a pair. So it sees 2 in each one of those lines, but it only actually owns 1. So that's where we get it. Our electronegativity difference in this case is going to be N minus N. Again, I'm not sure. I want to guess it's about 3.06 maybe, or 3.16 or something like that. Either way, it's going to be identical. And I'm going to get an electronegativity difference of 0. That's your answer. This may not be right, but you're going to get 0. This is purely covalent. And I don't need partial charges.